All right, so another thing that spontaneity helps, or sorry, another thing that thermodynamics help us talk about is what we call spontaneity, a spontaneous reaction. Now, a spontaneous reaction is a reaction that is going to occur without any continual intervention. The reaction will just start right away. The reaction will proceed as we write it, left to right. Okay, so if a reaction is spontaneous as it's written left to right, that's what we're talking about, because reactions can be in equilibrium. They're not always accompanied by necessarily an exothermic process, meaning that they're releasing heat energy, but usually they're going to be related to a release in heat energy. Okay, you can tell if a reaction is or a chemical shift, a chemical change is spontaneous, because if you put the chemicals together, then that chemical change will occur, right? That's an indication that a reaction is spontaneous. All right. Now, the driving force for a chemical reaction to proceed spontaneously from left to right is driven is that it releases energy, either heat energy or work energy, right? And the reason why that is a driving force is because as that process releases, as the process forms new bonds that are more stable, that is what causes that heat energy to be released. And the other parameter that is related to whether a reaction is spontaneous is what we call the entropy. Now, I think you guys have heard of entropy before in some biology classes, where it's described as the measure of randomness. So if we look at a reaction or a chemical condition like this, where all of our elements, compounds, whatever entities here are separated and moving around, and then we kind of bring them together, what we're doing here is we're decreasing the randomness, right? And if we wanted to look at the change in entropy, we'd have to think of this system as being what? What do you think, more or less entropy?
That's more random. Does that mean more entropy?
That's right. More random means more entropy. So here we have less random, more ordered, and a lower entropy. Now, we actually quantify this. So let's give this one a number. What's the number, Fred?
What do you mean?
Give me a number for entropy for this system here.
100?
All right, that's fine. So if this is 100, the system over here on the right, and what are we going to call this system over here?
500?
Okay, so 500 on the left. If the system reaction changes from this one to that one, right, we have become more ordered, all right? So therefore, the final 100 minus the 500, 100 minus 500, final minus initial, right? That would be the change in entropy would be equal to 400, right? 100 minus 500, sorry, negative 400. Okay, whoops. But this sort of change, if something is disordered and going to more ordered, that requires energy from the surroundings. All of this system has to come together to order itself. And so we have an issue associated with our signage there, because this is not spontaneous for a reaction to become less ordered and go more ordered. That would not be considered naturally spontaneous. Okay? So we have to fix that, and we'll show you how we fix that in a minute. Let's talk more about entropy here. So here we have an entropy associated with these particles confined to this region. As we open it up and give them more space, now there are more what we call, whoops, the other way, there are more probable outcomes, more ways that these particles can kind of move around, more places that they can reside, more neighbors, or not more neighbors necessarily, but more spaces that they can find different numbers of neighbors in. Okay, so here we have the same number of materials, but it's confined to a smaller area. So increasing the area can be a way of increasing our entropy. All right, here's our solid, liquid, and a warmer liquid, right? The motion. If you can't move, if everything's solid, your entropy would be low, but as more motion is possible, you have a higher entropy. Okay, mixing. If I have two chemicals that are separated from each other, there is a collective entropy of those two chemicals, but when I mix them, there are many more ways in which the chemicals can interact, and so I have an overall increased entropy. Okay, so with that in mind, we could think of the state being a way to indicate to us the relative entropy. So what do you think would have a higher entropy of the same chemical, a solid or a liquid?
Liquid, it can move around more, so it would be higher entropy.
Very good. So state is a way of kind of relatively thinking about entropy. Number of particles. Number of bonds could also be a way of thinking about entropy, right? And we could think about the entropy of a pure crystalline solid at 0 Kelvin as defined as 0, perfectly ordered. All right? Okay. Now, let's predict the sign, then, for these entropy changes. Now, I should have left this up here. Remember, we had a negative 400 if our system went from high entropy to low entropy, right? We had a sign of negative 400, right? Now, when we say low entropy, right, did that mean more ordered or less ordered?
The lower sign was more ordered, right?
Lower value is more ordered.
Yeah.
That's right. So 100 would be more ordered than 500. Okay, so if dry ice, which is a solid, goes to carbon dioxide gas, would this process be getting more ordered, going from left to right, or more disordered?
That'd be more disordered.
That's right. So would you expect the delta S to be positive or negative?
Let's see. Down there was negative, so positive?
Okay, very good. How about this one? Moisture condensing on a cool window.
You're going from like a gas to a liquid, right?
That's right.
So that is gas going to a liquid. That's more order. So that's a negative sign?
That's right. Negative delta S. Good. How about this reaction?
What is AB? Is it a solid, liquid, or gas?
Well, we don't always, that's not always our only indicator of entropy, right?
Oh, yeah, okay. So, well, you got one thing, and now you're on the reactants, and you got two in the product. So that's increasing entropy, right?
Very good. So if it's increasing entropy, is the entropy sign going to be positive or negative?
It's going to be a positive sign.
That's right. So, for example, give me a number for this.
100.
Okay, how about a different number? A number that's different than this 100 down here.
Oh, 10.
Okay, so this is 10. Is this going to be higher or lower than 10?
Higher.
So maybe 20?
Sure.
So 20 minus the 10, that would be a positive value. Now, how did I know that this was a higher value?
Because it's more disordered.
That's right. Okay, how about a drop of food coloring added to a glass of water as it disperses?
That's going more disordered, so positive.
Very good. So here's a solid combining with a liquid to form more solid.
All you get at the end is solid?
Yeah.
So that is going more ordered. So that's negative sign.
That's right. Delta S is a negative value there. Okay, good job. Good introduction and reminder about entropy.